So this is section 14.2, which is on double integrals and polar coordinates. So for an intro, let's think about what we know so far. We know that to evaluate a double integral, we convert it to an iterated integral, and how we do that depends upon the region R. Right? So in other words, to evaluate one of these guys, it depends upon R. So far we only have two options. We have vertically simple and horizontally simple. But it's very often the case that neither of these is nice. So sometimes neither is ideal, let's say. So let me give you just a simple example. I'll give you a simple example and a worse example. So basic circle centered at the origin. So let's say this is the circle x squared plus y squared equals, let's say 25. It's filled in, so really it's less than or equal to 25, but that's right. So this is therefore radius 5, x-axis, y-axis. So as a vertically simple region, the x's go between -5 and 5. If we were doing an integral, we'd end up with something like this, -5 to 5 for the x's. For the y values, we'd have to solve for y in the function, in the red equation rather, to get a positive and negative. And so we'd get negative square root of 25 minus x squared and positive square root of 25 minus x squared. And then whatever we're integrating, and then dy dx. Now those square roots are not particularly nice. If we did horizontally simple, then the y values would go -5 to 5. The x values, we would solve for x in that function. Oops. Get 25 minus y squared and plus square root of 25 minus y squared. Then whatever we're integrating, and then dx dy. So the thing to see here is that neither of these is particularly nice, right? Because they all have this sort of icky square root in them. They're not wrong, but they're just sort of unpleasant. And an even worse case scenario would be something like this. Like what if we offset the circle slightly? So this is the circle. This should have been red. That's okay. We'll shade it in. So this circle, this is centered at 1, 0. So as an equation, this is x minus 1 squared plus y squared equals radius of 1 squared. And so if we wanted to do that as a vertically simple region, we have to solve for this y, right? This is particularly icky. This is y squared equals 1 minus x minus 1 squared. So y is plus or minus the square root of 1 minus x minus 1 squared. That would need to show up in our integral, right? We'd have to do something like this as a vertically simple region. Our x's would go 0 to 2. Our y's would go from negative square root of 1 minus x minus 1 squared to positive square root of 1 minus x minus 1 squared. Whatever we're integrating, and then dy dx. That is really, really atrocious. And as a horizontally simple region, it's even worse. So neither of these is nice. So isn't there a better way? So the reason we believe there is because these are simply circles. So I feel like It seems like if circles are nice, they should lend themselves to nice double integrals. And so the problem is, of course, that circles are not nice in rectangular coordinates. Or let's say they're less than ideal. In rectangular coordinates. But in polar coordinates, they're much nicer. So what we'll do first is we'll do a really brief review of some polar coordinate shapes. And then we'll talk about how to describe regions in polar. And then we'll talk about what that says about integrals. So we'll say very brief review. Say brief polar review. So I'll just do a few examples of describing just some circles, a couple of cardioids, things like that. So circle like we have on the left. First one. This guy. Radius 5. This is the circle, r equals 5. So notice r equals 5. Theta is anything. Remember, theta is the angle around from the positive x-axis. So I'll say note here, theta goes between 0 and 2 pi. That gives us that circle. The second circle that we have here, the one lower down, this guy, it's also not so bad. Let's say it goes out to 2. There's the circle r equals 2 cosine theta. And this is for angles here. Negative pi over 2, less than or equal to theta, less than or equal to pi over 2. If that's a bit fuzzy, the way to remember that is that there's only circle between here and here. Those are the theta. These are the theta for which we have circle. Well, let's say theta we have stuff for is over here. There's nothing over here. Not a thing. On the other picture, of course, we've got stuff all the way around, right? We've got circle between here and here. But on the right-hand side, it's just half of it. It's from negative pi over 2, which is down at the bottom, down here, and pi over 2, which is up here. So that guy has a friend, which is a circle that is above here, above the x-axis. That is right here. Let's say its radius, now let's say it goes up to y equals, say, 7. This is the circle r equals 7 sine theta, and here note that theta goes from 0 to pi. And we've got a couple of other ones. We've got 2 cardioids. We draw the axes for these two. So the first cardioid is this guy. So let's say if it goes here to, say, 6, 3, and 3. This is r equals 3 plus 3 cosine theta. This is theta goes from 0 to 2 pi. And this one goes above. There are a few other options, but this is good for now. This is r equals 3 plus 3 sine theta 0 to 2 pi. So a couple of other things that we need to look at, but These are the ones to know first, and then we'll hit some of the other ones as we go. So we've got, just to summarize so far, we've got this note about sometimes neither vertically nor horizontally simple is ideal for describing regions, but polar may do the job, and here are some classic shapes in polar. So what we'll do next is we'll look at how to describe a region in polar. Once we know how to do that, we can discuss integrals. So going back over here on the left, let's say describing an R in polar. So here's the way to think about it, is whenever you're describing a region in polar, put yourself at the origin. So then the way it works is as follows, is you'll have two angles, alpha and beta, that the region lies between. So R will lie between two angles, alpha and beta. Remember, those are measured from the positive x-axis. And then between those angles, what we'll have is we'll have near and far polar functions. So by near, I mean near to the origin. And by far, I mean far from the origin. And by polar, I mean of the form R equals ... So a really simple rudimentary picture, and then we'll look at some specific examples, would be something like the following. Like, so I have an angle alpha, I have an angle beta. Within those I have a near function that's near to the origin and a far function. So, and then the region is the stuff that's in there. So just to label a couple things here, this right here, this is the near function. This will be R equals something. And the far function, R equals something. And then those two angles are measured from the positive x-axis. So for example, the alpha is measured right in here. I won't label the beta, but that would be the alpha. So here are some specific examples. Like, we'll do a really, really easy example first. So something like, let's say, a circle with a hole in it, like a washer shape. It's a really, really easy first shape to do. Like this R right here. We'll make the radio really nice. We'll make the radii rather 2 and 1. So for this particular guy, we're going to have, it goes all the way around. So alpha goes from 0 to, or theta goes from 0, which is alpha, to 2 pi. That's the whole way around. Then we have the near function, which is R equals 1, that's the inner circle, and the far function, it's R equals 2, that's the outer circle. So these are the criticals. These are the things to keep in mind. These things describe this region. So let's look at a few more examples. All right, so a few more examples. Do a another really easy one. Suppose we just had a quarter of this annulus, quarter of a washer. Like this. Say radius 1 to radius 3. That's nice and easy. Here we have alpha equals 0, beta equals pi over 2. We have near function R equals 1 and far function r equals 3. So that's the data for this r. We do two more. So suppose we had something like, so I'm doing combine a couple of things. So we'll have two circles. They won't be centered at the origin now. That'll be a little different. So first one will be one of these. Well, they'll both be circles like this. We saw these on an earlier page, and the stuff will be between those. And so they'll go from, say, 1 to 2. So the thing to remember about these two circles, well, we'll get to this in a second. So in this case, everything's to the right-hand side of the y-axis. So alpha is negative pi over 2. Beta is pi over 2. The near function. So remember, near is always from the point of view of the origin. I'm going to decorate this picture in a minute so we can see. So this will be r equals 1 cosine theta, or just cosine theta. And far will be r equals 2 cosine theta. So if that data is unclear, take a second look at the picture. I'm going to draw all over it. So the way to see this is the angles are because the stuff is all the way around here. But just that, right? There's nothing over here. So this is 0 or negative pi over 2 at the bottom to pi over 2 at the top. Within those, if you dump yourself at the origin right here, and you look out over this region, so suppose you look down here, you see two functions. You see this function first, that's the near function. That's r equals cosine theta. And then you have your far function, and that's r equals 2 cosine theta. So that's the way we're determining near and far. It's from the origin. And this is the same no matter which way you look. If you look up here, near function, far function. That's where those come from. So one more example will be something like, let's say, sorry, that should all be in red. Let me just shade it in red. So the region is this region up here. So I'll make this go to, say, 4, and this will be at 2. So we'll do a little bit more work for this. So here things are not so obvious, right? So what we can look at is, what we'll do first is we'll look at the near and the far functions, right? So if we put ourselves at the origin right here, and we look out over this region, like right there, we see a near function right here and a far function right here. So one of these is a little easier than the other one. So the far function is this guy right here. So far function is the circle. This was the circle that we saw. This is r equals 4 sine theta. So that's fine. Right? This near function right here, this is the line. The line is the function, or we think of it as y equals 2, but the problem is that this is not polar. So then what we need to do is we need to remember a couple of facts. So recall that when we convert to polar, we have x equals r cosine theta and y equals r sine theta. So in this case, y equals 2, this converts to r sine theta equals 2, or r equals 2 cosecant theta. So that is our near function. Then for our angles, alpha and beta, these occur where the two meet. So on the picture, I'm going to totally trash this picture, I apologize. Those angles will be here, that's our alpha, and here, that's our beta, because there's stuff all the way between those two, right there. Right? There's nothing outside of that range. So if we want to see where they meet, we need to set them equal to each other. So that would be where 4 sine theta meets 2 cosecant theta. So cosecant is 1 over sine. So if I multiply both sides by sine, we get 4 sine squared theta is 2. So sine squared theta is 1/2. So sine theta is plus or minus root 2 over 2. And this happens at angles of pi over 4 and 3 pi over 4. Now on this picture it's actually not so hard to see because the points where they meet are 2, 2 and -2, 2, so it's a little easier to see, but there's sort of a little more formal way of finding it. So here's the practical upshot of all of this. So what I'll do is let me redraw this whole picture so it's a little bit prettier, a little bit bigger, so we can really see. So we've got our circle, got our line, we've got our region, we've got our angles, which go from alpha, which is pi over 4, to beta, which is 3 pi over 4. And between those, we've got our near function and our far function. And so in this case, put it all together, we've got alpha equals pi over 4, beta equals 3 pi over 4, near, which is our line, which is r equals 2 cosecant theta. We've got our far, which is our circle, which is r equals 2 sine theta. That is the data that draws this r. So the critical thing to see before we go any further is these 4 things, right? The alpha, the beta, the near, and the far. These are everything, right? Finding these is the hard part, or is the important part. So finding alpha, beta, near, and far is everything, as we'll see. So once we know those, then iterating the integral makes sense. So that's what we'll do next. All right, so here's the deal. I think I'm on number 4. Hopefully it's number 4. So evaluating double integrals in polar. So here's the fact. This will say, suppose R is described using those 4 things. In other words, using alpha, beta, r equals near, and r equals far. So like over in the previous example, just like that. So then what happens is, if we're trying to evaluate this guy, remember this was the original goal. So a few things happen. It's a little sneaky. So the first things, the integral itself is pretty straightforward. The outside integral is always theta and goes from alpha to beta. The inside integral is always r and goes from near at the bottom to far at the top. Then we have the function. Now the kicker is the function is a function of x and y, and the integral is going to be an integral of r and theta. So the x and y have to be replaced. So using the conversion to polar, we convert our x to r cosine theta and our y to r sine theta. Now, when we do this, there's also an additional change that occurs. and this won't make a lot of sense now, but it's we cannot forget it, is that we pick up an additional r. And so that goes in, and then we have dr d theta. A couple notes before I give an example is one, what's happening here is replace x by r cosine theta, replace y by r sine theta, and then there's another conversion thing that's nice for polar, is that x squared plus y squared equals r squared. So if you ever have an x squared plus y squared, you can replace it by r squared. Then over here, this guy appears. There are a couple of things we can call it. Later on, it's going to be something called a Jacobian. So you can think about it. You could call it the polar r, or you could call it the Jacobian. The thing is, for now, is don't forget it. It'll become clear later on in the section, I think 14.8, why this is necessary, or where it comes from specifically. The thing is that this new integral is now an iterated integral in r and theta. So the result is an iterated integral in r and theta, which we then evaluate. So really simple example. I'm not going to evaluate this one. I just want to do it while there's other pictures on the screen. So let's say in the previous picture, let's say with the previous r, like this guy over here. If we wanted to evaluate, let's say to evaluate this integral over r of, say, x squared plus y squared dA, we simply do the integral over r of x squared plus y squared dA. This would become pi over 4 to 3 pi over 4. The near function is 2 cosine theta, or sorry, 2 cosecant theta to 2 sine theta. The integrand, the x squared plus y squared, becomes r squared. Then we pick up the polar r, the new r, and then dr d theta. So I'll do a nicer one in a second that we can actually evaluate. But in theory, we evaluate with respect to r, we plug in. We evaluate with respect to theta, we plug in, and then we finish. So let's work out a nicer example right now. So going back over. So for example, we'll do like a really, really simple example. Let's say evaluate, say, the double integral over r of x squared plus y squared dA. So same integral as before. Well, but we'll do just a really simple circle for the r. So something like circle of radius 2. So the fact of the matter is we won't actually do that much integration. The integration itself is usually done by computer. It's the setting up of the integral that is something that the computer can't do. Like, we cannot just feed it this data and have it figure out the iterated integral. So the hard part for us as the humans is getting the iterated integral. Then you can chuck it into MATLAB or R or whatever software that you're using. So for the solution here, what we do is we look at the circle and we go, R is described by, so we have alpha equals 0, beta equals 2 pi. We have near, which is r equals 0. There's no inner circle. We have far, which is r equals 2. That's everything. That's the critical stuff. So this guy, this integral, then simply becomes the integral from 0 to 2 pi. From 0 to 2, x squared plus y squared becomes r squared. We have a polar r, dr d theta. So we just charge ahead. So 0 to 2 pi. This is an r cubed, so we integrate that, get 1/4 r to the 4th plug in 2, plug in 0. So when we plug in 2, we get 16 over 4. That's 4. Plug in 0, we get nothing. Integrate that with respect to theta. Gives us 4 theta. Plug that in. And we get 8 pi. Don't worry about what that means right now. Just look at the mechanics of the integral. So the critical thing, just to review here, was getting this data. Right here, circled in blue, is what are the 4 critical things that describe the region. Once we have that, those are what get us down to the iterated integral. And then it's just calculation, which may not be pleasant, but there's not a lot of thinking involved in the same sense. So let me do just one more that actually has a specific, let's say, volume in mind, because originally we're talking about volumes when we calculate these. So this one I won't necessarily evaluate to completion, because setting it up is the important thing. So let's say find the volume of the solid under, let's say, the plane C equals 10 minus y above the x-axis, above the xy plane rather, and inside, let's say, the cylinder x equals r, or let's say, sorry, inside the cylinder r equals cosine theta. So there's a lot going on here. So just to explain, so we're actually getting a little bit ahead of the game here. So when we say the cylinder r equals cosine theta, what we mean is the following, right? So r equals cosine theta is this circle. In 3D, this is a cylinder. So that cylinder looks like this. So notice it's on the, it's sort of to the right of the y-axis, which means it's forward in the picture here. The z is not given, so z could be anything, which is why it extends up and down. This is sort of really cylindrical coordinates. We're a bit ahead of the game, but that's okay. Hopefully this will make sense. And so the overall picture, and then this plane, z equals 10 minus y, this has a z-intercept at 10, and then as y increases, it goes down. So this guy looks like, so sort of angles down in the y direction, goes through here at 10. There's this y-axis label down there. So the overall picture of this, let me do the best I can do, is we've got the cylinder right here. We've got, I'll draw the rest of the cylinder in a second. We've got this plane that goes like this. The cylinder comes up, it hits the plane in a circle. And the thing that we're interested in is this volume that's in here. So the plane is on top. And of course we're above the xy plane, so down here the xy plane is in the bottom. So what we need to do is we need to think about this as a function defined on a region. And so you can kind of see this pretty easily, but let me redraw the picture so we can perhaps see it even more easily. So going back to the left, right? So let me just redraw this picture. I want to redraw it so we can really sort of figure out, make sure that we're clear on what the R is. And so I'm going to kind of redraw it, like I'm going to think about it differently a little bit. So the R in this case is this region down here. The function that everything is under is, of course, the plane. Right here. This is our f of xy is the plane. We've got x, y, and z, and the volume that we're looking for is the volume that's under the plane and above the region. It's that guy. That's the guy we want. So let me just label a couple things. This is the R. So what we're looking for here, abstractly, is we want the volume under the plane and above R. Right? So what that is, abstractly, is the double integral over R of the plane. So the plane is 10 minus y dA. So that should even make sense in the context of 14.1. We've got an R in the xy plane. We've got a function lying above the xy plane. That's our f of xy. That's this guy. This z equals 10 minus y, or f of xy equals 10 minus y. And we want the volume underneath it. Now, of course, here, if we redraw R, we draw R in the xy plane alone. In the xy plane alone, R is this thing over here. We can see that this is this picture right over here. It's that cylinder. It really R is the inside of the cylinder because we want the volume above it. This goes out to 1 because R equals cosine theta goes out to 1. This is on the xy plane. And this guy, we saw something like this. This is described by, this has alpha equals negative pi over 2, beta equals pi over 2, near r equals 0. There's nothing near to the origin, far as r equals cosine theta. That is everything. That's the critical. So then this thing that we want to evaluate, integral over r of 10 minus y dA. We put in the alpha and the beta. We put in the near and the far. We substitute in, so we have 10 minus y, but y is r sine theta. We put in the polar r, dr d theta. So just to clarify a couple things, this guy right here, this is the 10 minus y. This guy right here, he is the polar r. And then we just evaluate. It's not pretty. That's all we do. So that's pretty much it. Actually, let me just do one more example. So we'll end on a really easy note. We'll say find the volume of the solid under the paraboloid z equals 9 minus x squared minus y squared, and above the region, and I'll just draw the region. So the region will be, say, this region. That should be in red. That's terrible. That's all right. This one will be in black. So it's this half circle that's to the right of x equals 1. And so the paraboloid is above the xy plane. We don't need a picture of this to do anything, to do the problem, but no harm in doing a picture. So the paraboloid is this thing. The r that we just drew is sort of over here. So the solid, it's really hard to draw here. In fact, it's easier to integrate than it is to draw. It's like this half circle shaped thing that's lying above here. So it's a bit confusing. However, we know that the volume abstractly, or symbolically if you like, is just the double integral over R. This is the R right here. This should be in red. I apologize. Of the paraboloid, which is our 9 minus x squared minus y squared dA. So really the kicker is, like, how do we describe R? So R is this shape up here. So let me redraw R just so we can be really, really clear about it, because that's where everything important comes. Let me draw it in red so we're all on the same page with the colors. So that is our R. So we played this game before with figuring out what these values are, right? Well, it's something like this. So for the near function and the far function, we can look at these two, right? So the far function is the easiest one. Okay? This far function is R equals 2 cosine theta. The near function is the line x equals 1, which gets converted to R cosine theta equals 1, which is R equals secant theta. The angles are plus and minus pi over 4 here. So in other words, alpha is negative pi over 4 and beta is pi over 4. You can find these either by setting the 2 cosine theta equal to the secant theta, or in this case, this isn't so bad to see because these are in nice positions, right? These angles, this angle is 45 degrees down. This angle is 45 degrees up. That's our beta. So it's pretty easy to see. Right. Or again, you can find those. Let's just be clear. Can find alpha and beta by doing 2 cosine theta equals secant theta. Those are the two places where the curves meet. Right? In any case, we have the 4 critical things. So what we have is the volume that we want. This guy then gets iterated. We go from negative pi over 4 to pi over 4. We go from the inner function, which is secant theta, to the outer function, which is 2 cosine theta. The 9 minus x squared minus y squared becomes 9 minus r squared. That gets multiplied by a polar r. And then we have dr d theta, and that's the end.